All right, guys, the last biochem lecture we have to do is enzymes. Enzymes are important because they help every reaction in living things occur at a speed which enables you to continue living every time. All right, so what's an enzyme and what's an active site? An enzyme is a globular protein, it's in the quaternary phase, that accelerates a specific chemical reaction. So at the SL level, we say one enzyme, one reaction. At the HL level, we do a little different. At the HL level, we say that some of these enzymes have the ability to adapt. And so it could be one enzyme, multiple reactions. And we believe that is like more the current research, current idea, because your body is an efficient organism. And it's really inefficient to have to make a single enzyme for every single reaction in your body. It's more efficient if one enzyme can be produced and then catalyze multiple reactions. So a biological catalyst is something that speeds up a reaction without changing the actual reaction. Enzymes are not used up in the reaction, they're used over and over and over again, which means you can make that enzyme once and use it for a long period of time. The active site is the spot on the enzyme where the substrate binds. The substrate is whatever the enzyme's working on. So again, at the SL level, enzymes are reaction specific. The shape of the active site is so specific that only one enzyme can catalyze each reaction. And it's like a lock and the key, where the substrate fits into the lock of the enzyme and it only fits into that one lock. We measure the speed of an enzyme reaction in two ways. We can measure how fast does the substrate disappear and how fast does the product appear. So how quick are we using up the substrate or the reactants, and how fast are we getting the product on the back end? So here we go. This is what your protein looks like, what your enzyme looks like. And as it has folded and combined in that quaternary phase, it makes a spot for your substrate to lock into it. I'm just gonna go back to this. Some of you guys heard this freshman year, but the way I like to describe an enzyme is like a dating site or a dating app. So out in the world, you have these substrates and they're out there and they're bouncing into each other. And if they bounce into the right one, a reaction might happen. But it's all about luck, right? You are lucky that you bounce into it. It's kind of like you guys in a dating world where you're out there and you're meeting people and maybe you get lucky and knock into someone that's got all of the same qualities that you want in a significant other, and you guys join together. But there's a lot of effort put into that, right? You've got to get dressed, you got to leave your house, you got to go out places to like movies and to dances, and oh my gosh, it's exhausting. That's the same thing for these substrates, right? They got to go out and there's a lot of energy put into it to make them move around so that maybe they knock into each other. But if you go on a dating site like Christian Mingle, for example, then you are narrowing it down and you're getting only people that have the same likes and same interests that you do. You're sitting on your couch in your pajamas, very little effort is going into this, and chances are you're going to find a match. It's specific, just like the dating sites are specific. So Christian Mingle, only for Christian. Farmers.com, only if you want to be a farmer. So our enzymes are specific to a specific type of substrate, just like your dating sites are specific. What the enzyme does is cut down on the amount of energy necessary for this reaction to occur. It makes the reaction occur easier. So what are the effects of some of the things on the enzymes? Well, temperature, we talked about proteins will denature if they hit too high of a temperature. Below the optimal temperature, it's not denatured. That enzyme is working perfectly well, but the molecules, the substrate's moving around so slowly that the odds of it locking into that enzyme are low. And so your reaction rate is low. When you hit the optimal temperature, everything is moving just the right speed. The enzyme is in the perfect configuration, and bam, we get a lot of product. If you go above the optimal temperature, the enzyme like falls apart and that active site disappears. And now you don't get any reaction at all. So below optimal temperature, the enzyme is still functioning. It's not denatured, but things aren't moving fast enough to find each other. Above the optimal temperature, now your enzyme doesn't have its shape anymore. The active site isn't there. Most of the enzymes in your body work at body temperature. Makes sense, right? So the optimal temperature is around 37 degrees Celsius. pH is another one where you have to have an optimal pH. Below the pH, things don't work. Above the pH, we denature and the active site's gone. And so we want that active, perfect, optimal pH. So here are some of the ones that you need to know. Pepsin is in your stomach. Well, what's the pH of your stomach? It's 2. So the optimal pH of pepsin is 2. You put pepsin in 7, it's not going to be efficient. You put pepsin in 1, and it's going to denature. In your intestines, we have this trypsin, and that's working at like a 7 to 8 because that's the pH of your intestines. The effect of increasing substrate concentration, you will increase the rate of reaction as you increase the rate of substrate until all of your enzymes are busy. And then it levels off because once all of your enzymes are busy, it doesn't matter how much other substrate you put there, the enzymes are all busy, and so they can't do anything. So again, as substrate concentration increases, rate of reaction increases until you hit maximum, and then it levels off because all of your enzymes are busy. We're going to use these enzymes for commercial purposes, so we can trap enzymes on a bed of calcium alginate to ensure that they can be reused so that they're not washed away. All of your clothing detergents have enzymes in them, and there are enzymes that will break down the proteins in grass and the proteins in blood, and this is what makes your clothes clean. In fruit juice, we're going to use pectinase, which is an enzyme. This is going to separate the juice from the cells. It's also going to take the cloudiness out of your juice and make it clear. Baby food, we're going to pre-digest the big proteins with enzymes and make them smaller so that the baby can digest it easier. And if you are lactose intolerant, you can pre-digest the lactose in your milk by adding lactase in a commercial vat, and then you get lactose-free milk. So the idea of lactase, I mentioned it earlier, 70% of the world's population is actually lactose intolerant, which means they cannot break down the protein that's in milk. And if your body can't break it down, your body gets rid of it as fast as possible. So throwing up, diarrhea, upset stomachs, gas, that's a normal condition for 70% of the world's population. The ability to break down lactose, that making of the lactase enzyme, drops off around age 2. That's a pivotal age because that's the age at which point most humans stop breastfeeding. And so then you don't need the enzyme to break down milk because you're not getting it. Look at our breakdown here. 100% of Native Americans are lactose intolerant, 75% of African Americans, but only 2% of Swedes. Well, what did the Swedes have that the African Americans and the Native Americans didn't? They had domesticated cattle. And so they, in times of famine, would take the milk from the cattle and utilize that as a supplemental food source. And if you could break that down, you had a greater chance of surviving. And so the ability to produce the gene later into life stayed with you because there was an evolutionary benefit to it. The milk industry has made it possible for lactose intolerant people to drink it by creating products that have lactase in it already. And so when you buy the lactose-free milk, it's already been pre-digested for you. You can buy the lactase enzyme in tablets. And so if you like really want that pizza or you want that ice cream, before you eat it, you take a tablet and it will help you digest the milk. Here is just that movement of the ability to break down lactose. Okay, HL, material. Difference is, again, enzymes are not as specific. Enzymes are used in metabolic cycles. These pathways in the cells are chains and cycles of enzyme catalyzed reactions. So the two that we think of most frequently are cellular respiration and photosynthesis. Use enzymes embedded in the membrane of the organelles responsible for those procedures. in order to do the process of cellular respiration and photosynthesis. Metabolic reactions rarely occur spontaneously, and so we need enzymes in order to do these reactions. And here are all of the enzymes that are responsible for cellular respiration. Look, every single step has multiple enzymes. Thankfully, y'all don't need to memorize all of these. There'll be a couple when we get to cellular respiration and photosynthesis, but not all of these, not until you get to your graduate work. The idea of the induced fit model is that idea that multiple substrates can fit into one enzyme, that enzyme is going to adapt its shape. This allows multiple substrates to fit, allows one enzyme to catalyze multiple reactions, allows your body to be super efficient. Enzymes lower activation energy, so it takes less energy for a reaction to occur if you have enzymes present. We've kind of gone over that already. And this is just the picture of it. Without an enzyme, you have to get all of this energy in order for the reaction to happen. With an enzyme, you can see it cuts down on the energy required. Inhibition is a way of stopping an enzyme-driven reaction, and we have competitive and non-competitive. Competitive inhibition is you have the inhibitor that is trying to lock in at the active site. It is actively competing with the substrate. If I increase the amount of inhibitor, I decrease the reaction rate. But vice versa, if I increase the amount of substrate, there'll be more substrate than inhibitor there, and so the reaction will occur. The enzyme remains active in a competitive inhibition type environment. Non-competitive inhibitors are going to lock in somewhere away from the active site, and when they squeeze in, they change the shape of the active site, and because the active site's shape has changed, your substrate can't lock in anymore. It basically makes the enzyme ineffective. Doesn't matter how much more substrate you add, the active site's not there, so the enzyme's not going to work. And here's just the pictures. Non-competitive locks in away from the active site. This is the active site right here, changing the shape, whereas a competitive locks in at the active site, blocking the substrate. We have this idea of in-product inhibition. In-product inhibition is where the product that is being made acts as an inhibitor in that reaction. All right, that's kind of confusing, but let's think about it this way. Often we see this in cellular respiration, and the end product of cellular respiration is ATP. So let's say I eat my donut, and then I am a slug on the couch. And so my body is breaking down glucose to make ATP, and it makes enough to keep me alive, but then it goes, well, wait a minute, she's not doing anything. She doesn't need all of that energy from the donut. And so I'm going to stop this process. And the excess ATP actually locks in at a non-competitive site, changing the first enzyme in this change, or in this chain. And so now the glucose can't lock in, the glucose can't be turned into ATP. That glucose is then stored for later. And I get fat because I'm sitting on the couch. But let's say my husband goes, come on, time to go, let's go run. I'm like, oh, fine, whatever, I'll turn off Netflix. And I get up and I start moving, and now my body goes, whoa, we need more ATP here. The first ATP that is used is that one that's over in the non-competitive inhibition spot. And so it yanks that ATP out and uses it. Now the chain is open again, that enzyme is functionable, and my body can start breaking down glucose. Tons of videos here to watch. If you are a Mrs. Miller person, you came from AP Bio, you are familiar with Bozeman. Bozeman's got videos for all of this.